Hey everybody, welcome back. In this lesson we're going to continue to work with radicals. Specifically, one main skill from this lesson, I want you to be able to simplify a radical expression. Oftentimes we end up with a root that isn't written as simply as it can be, so we're going to use the product rule for radicals in order to simplify roots. We'll do that by factoring the radicand into smaller pieces, and then we'll also look at the quotient rule for roots to see how to simplify fractional roots. So let's get started. Okay, so all of our work today is going to be based on one important fact here, and that is what we call the product rule for radicals. What it means is that if you have a root of some kind of a product or something that you can split into factors, you can do that, and it splits into two separate roots. The key is here that that works for things that are multiplied together. It does not work for things that are added together. So I want to just make sure to caution you about that. It is certainly true that if you multiply things together inside the root sign, then you can split it into separate roots. And in fact, you can do the opposite. You can multiply individual roots together into a single root. We'll work with that more in our next lesson. But it is not true that if two things are added together, that you can split those up into separate roots. Those are not equal. And in fact, you can see that with numbers. The square root of 2, which is equal to the square root of 1 plus 1, is definitely not equal to the square root of 1 plus the square root of 1, because the square root of 1 plus the square root of 1 is 1 plus 1 or 2, and that's not equal to the square root of 2. So be real careful of that. Let's take a look at some examples. The square root of 12. Now we can split that up any way that we want, but here's the key. You're always looking for things where you can take the square root. So for example, 12 breaks into 4 and 3. So we're going to break that into the square root of 4 times the square root of 3. And the advantage there is, of course, we know what the square root of 4 is. The square root of 4 is 2, and so we can then write our result as 2 times the square root of 3, and we have simplified that. Now don't take my word for it. Pull out your calculator and check these two things. If you evaluate the square root of 12, you get 3.464. That's an irrational number. It goes on forever and never repeats. And if you take 2 times the square root of 3, you get 3.464, the exact same number. The square root of 12 is the same as 2 times the square root of 3. So why is this way better than this way? We'll define that in just a minute. Let's do a couple more examples, but we're going to say exactly why this way is better than this way. Okay, the square root of 98. Well, you got to look for perfect squares that are factors of 98. So you start going through your perfect squares like 4, 9, 16, 25, 36. None of those are factors, but 49 is. The square root of 98 is the same as the square root of 49 times the square root of 2. And the advantage there is the square root of 49, we know what that is. That is 7 times the square root of 2. And so now we've simplified that expression. Now that works with other types of roots too. The cube root of 54. Well, now we're looking for any cube roots inside the factor of 54. So the cube roots like 1, 8, and the one we want is 27. So we would rewrite that as the cube root of 27 times what's left over? Well, 54 is 27 times 2, and so the other factor will be the cube root of 2. But we do that because we know what the cube root of 27 is. That's equal to 3, and so we end up with 3 times the cube root of 2, and we've got it simplified. Be careful, common mistake is to lose your index on these. So make sure that when you enter these in WebAssign, you include your index. And one last one here, negative 4th root of 48. So what are the 4th roots that exist in 48? Well, 48 breaks into 16 times 3, but we know what the 4th root of 16 is, so we're going to say that this is negative 4th root of 16 times the 4th root of 3. But we know the 4th root of 16 is 2, and so we would call this negative 2 times the 4th root of 3. Now you might say, well, 16 is kind of a hard 4th root to spot. You're right, and we're going to look at another way to figure out how that simplifies in just a minute. Before we do that, though, here's maybe the most important thing for you to be familiar with in this lesson, and that is when we simplify a radical, we say it's simplified when these three criteria are met. Powers inside your radicand, that is to say inside the root, are always less than the value of your index. There's no fractions or negative signs inside the root. And you can't have roots in the bottom of a fraction or in the denominator. We're going to focus on the first one right now. Let's see what we mean by each power in the radicand is less than the index. So if we start out with the square root of 8x to the fifth, as we've seen before, we always like to represent numbers as powers. So we're immediately going to change that to the square root of 2 to the third x to the fifth. Now, what's the index on this root? This is a square root, so the index is 2, right? We don't usually write that, but I'm going to for a minute. This is not simplified because our exponent, or our power, is bigger than the index. That should never be the case. Any powers inside the radicand have to be smaller than 2. And here's why. If we were to break this down, and I'm going to put extra steps that you don't usually need to do. If you were to break this down, you could say that that is 2 squared times 2, that's 2 to the third, right, times x to the fourth times x. Now, the reason I broke out the 2 squared and the x to the fourth is because we know what the square root of those are. The square root of 2 squared is 2, and then we'd be left with the square root of 2. And the square root of x to the fourth is x squared, and we'd be left with the square root of x. So when we simplify, the 2x squared comes out in front, and we're left with the square root of 2x. That is simplified because the 2 and the x each have an exponent of 1, and that's smaller than your index. So that is simplified. Now, let's do the exact same radicand, but a different index. What about the cube root of 8x to the fifth? Okay? If we were to do that, we would say the cube root of 2 to the third x to the fifth. But we know that we know what the cube root of 2 to the third is. That's going to be 2. That means that we would break this up and say the cube root of 2 to the third times x to the third times x squared. There's your x to the fifth. The cube root of 2 to the third is 2. The cube root of x to the third is x, and we're left with the cube root of x squared, and that one is simplified. Now here's a little shortcut. This is a little corny, but this is still how I think about this. When you go to simplify, think about the index as the bail that we need to pay in order to get out of jail, okay? And so the exponent is how much money each of these factors has. So if the 2 wants to escape, it's got to pay bail. It can because it has an exponent of 3. So it pays bail once and slips out to the front. And there's 1 2 left inside because we had a 1 power of 2 or $1 left over. X to the fifth, if bail is only 2, it can pay that twice. And so the x escapes 2 times, leaving us with x squared, and there's 1x left behind. Down here, we have the cube root of 2 cubed x to the fifth. The 2 has enough bail to escape. It slips out to the front. And x to the fifth, that has enough to make bail, and it pays it and escapes, but it leaves behind an x squared in the radicand. Let's take a look at one more with a negative sign. Okay, the second criteria for being simplified says that you cannot have fractions or negatives. We'll deal with fractions in a minute. But remember, if this was a square root with a negative inside, it would be imaginary and we wouldn't do anything with it at this point. We will later on in a few lessons. So if it's an even index, we really can't have a negative sign. And if it's an odd index, that negative sign is no problem. The reason it's no problem is if it's an odd index, we'll know what that root is. What is the cube root of negative 8? Well, that cube root of 8 is negative 2, right? Okay, and the cube root of x to the fifth, well, the x can escape once, but that's going to leave behind x squared. And so we end up with a negative 2x times the cube root of x squared, and we've got it simplified. Odd index, the negative will always escape. Even index can't be there, it must be imaginary. Okay, well sometimes it's not so easy to tell how to simplify or to break up that root, so we're going to use the prime factorization. A little refresher here because you've seen this before somewhere in your math history. Take the number 340. To find the prime factorization, that is to say all the primes that multiply to make 340, we make a factor tree. So what are two numbers that we could multiply to get 340? Probably the easy one to spot is 10 times 34. Now we do the same thing with these. 10 breaks into 2 times 5, and those are both prime, so we can't go any further. And 34 breaks into 2 times 17, and those are both prime. So we can conclude then that 2 times 2 times 5 times 17 is the prime factorization for 340. That's the most we can break 340 down into factors. So what that means is that when you go to simplify these roots, you can get a couple of different outcomes here. If we want to simplify the square root of 340, we don't necessarily have to spot perfect squares, we just write that using the prime factorization. The square root of 340 then is the square root of 2 squared times 5 times 17. Now, we just let large exponents escape. Our index here is 2, so the 2 escapes, but the 5 and 17 don't. So this becomes 2 times the square root of 5 times 17. Now be careful here. The 2 has enough bail to escape with an index of 2 just one time. Common mistake is to put 2 squared out there. 2 has enough to pay for one escape, so the square root of 2 squared is just 2. But the 5 and 17 are left inside, and those can go back together. 5 times 17 is 85, and so this simplifies to be 2 times the square root of 85. On the other hand, take a look at what we'd have here if this would have been the cube root of 340. Of course, we already know the prime factorization. That would be the cube root of 2 squared times 5 times 17. And notice now that the 2 with its exponent of 2 is not high enough to slip outside. It doesn't make bail, so it has to stay inside. In fact, everything does. And so the cube root of 340 does not simplify. Square root of 340 does, but the cube root of 340 does not. Okay, so with that in mind, let's pop through 3 more quick examples and simplify these 3 values. Now notice the instructions here say all variables represent positive real numbers. That just means we don't have to mess with any absolute value signs. We're going to assume that everything is positive here. So the square root of 150, well, let's do the prime factorization on 150. 150 is 30 times 5, but 30 breaks down into 6 times 5, and 6 breaks down into 2 times 3. So the square root of 150 is equal to the square root of 2 times 3 times 5 squared. But then you can see, since our index is 2, that the 5 escapes and the 2 and the 3 don't. And so what we're left with is 5, which escapes, and 2 times 3 is 6. 5 root 6. Cube root of 297b to the 4th. Well, let's do a prime factorization on 297 here. 297, that's 99 times 3. But 99 is 9 times 11. And 9 is 3 times 3. So we have 3 times 3 times 3 times 11. We can rewrite this then as the cube root of 3 to the 3rd times 11. That's based on our prime factorization, b to the 4th. And now we just ask ourselves what's escapes. The 3 escapes, and a b escapes, and we're left with the cube root, don't forget your index there, of 11. And 1b gets left behind, 3b times the cube root of 11b, and we're done. The 4th root of 224, s to the 8, t to the 7th, 224, let's break that down. Well, 224, if you're not sure, just find something that goes in there. That does divide by 2. It also divides by 4, so we'll break it down by 4 and 56. But 56 breaks down more, well, so does 4, and so we have 2 times 2 for 4. 56 is 8 times 7.
but 8 breaks down into 4 and 2, and the 4 breaks down to 2 and 2. So we can conclude that this is equivalent to the fourth root of 2 times 2 times 2 times 2 times 2 times 7. 2 to the 5th times 7, s to the 8th, t to the 7th. Prime factorization is useful. Now we can just see what escapes. The 2 is going to get out in front, and that will leave one of the 2's inside our root. The 7 will be left inside. S to the 8th, when the index is 4, s to the 8th escapes twice, so s times s, or s squared. That'll leave no s's inside. T to the 7th, the t escapes once, but leaves t to the 3rd inside. So we put the 2 and 7 back together. We have 2s squared t times the fourth root of 14 t to the 3rd, and we have that one simplified as well. Okay, it's your turn. Take a minute. I'd like you to simplify these to, here again we can assume that all variables represent positive numbers, so you don't need to work with absolute value signs at all. Pause the video and see if you can simplify those. Unpause to see those solutions. Okay, well, we need to do the prime factorization on 256. 256 is 16 times 16, which breaks down to 4 times 4 times 4 times 4, which breaks down again to 2 times 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 2. So cube root of negative 256 is the cube root of negative 2 to the 8th. Okay, well, remember, we cannot have negative signs inside, and since this is an odd index, we know what the cube root of negative 1 is. That's negative 1, so the negative sign just slips out in front. 2 to the 8th, index is 3. 2 can also escape twice, and so negative 2 squared, and that will leave behind how many factors of 2 on the inside? Well, if 2 escapes twice, if it pays 3 of its powers 2 times, that's going to leave 2 squared on the inside, and so this is negative 4 times the cube root of 4. Okay, well, 3 times the square root of 250, p to the 7th, q to the 10th. 250, that's definitely 25 times 10. 25 is 5 times 5, and 10 is 5 times 2. So we can rewrite that right off the bat then as 3 times the square root of 2 times 5 to the 3rd, p to the 7th, q to the 10th. Okay, this is a square root, so remember that's like having an index of 2. So here we go. The 3 is already out front. 2 stays. 5 can escape once, but that will leave behind one of the 5's inside. P to the 7th escapes 1, 2, 3, 4, 5, 6, 3 times. That's p to the 3rd, leaving behind one of the p's in front, leaving behind one of the p's on the inside in our radicand. And q to the 10th, if the index is 2, q to the 10th can escape 5 times, which makes sense because the square root of q to the 10th is q to the 5th. So we're all set. That's 15, p to the 3rd, q to the 5th, times the square root of 10p. And you've got it simplified. If you got both of those, nice job. Here's 2 more, though. Take a minute and see if you can simplify these. This time, we don't know that the variables are positive real numbers. This time, they could be negative. I would like you to use absolute value symbols when necessary. We haven't done that yet in this lesson, but see if you remember when they are necessary. Unpause to see how these work out. Okay, well, 135, we know that's divisible by 5, and so we get 5 times 27. 27 is 9 times 3, and 9 is 3 times 3. And so there we go. We can rewrite this as the fourth root of 3 to the 3rd times 5, x to the 7th, y to the 12th, and z. Okay, index is 4. The 3 does not escape. The 5 does not escape. X to the 7th, that has enough to escape once, and that will leave behind x to the 3rd. Y to the 12th, if the index is 4, that can escape 3 times, leaving y to the 3rd now on the outside. Makes sense. The fourth root of y to the 12th is y to the 3rd. and z does not escape, it's stuck inside. Cleaning this up, we get x y to the third times the fourth root. 3 to the third times 5 can all go back together. Turns out that 135 didn't simplify at all. X to the third z, and we've got that one simplified. Now, the question is, do we need absolute value signs on there? Well, we do. The root stays in the root, but since this is an index of 4, anything that was inside could have become positive or would have become positive, and so we should put absolute value signs on the things that escape. All right, our second one, the cube root of negative 32 a to the third b squared. I'm going to skip a little bit ahead here. We've worked with 32 a bit before. As it turns out, 32 is 2 to the fifth power, so this is really the cube root of negative 2 to the fifth power, a to the third b squared. Index of 3, what escapes? Well, we know that negative sign is going to escape since it's an odd index. 2 to the fifth, well, that'll escape one time, so we're going to have negative 2 out in front, leaving behind 2 squared on the inside. A to the third, that simplifies. B squared does not. And so when we're all done, we have negative 2a times the cube root, oops, I forgot my index there, don't do that, cube root of 4b squared, and we are all done. Do we need absolute value signs here? In a word, no. Why? Odd index. Odd indices preserve signs, so that negative sign slipped outside. No need for any absolute value signs. Okay, well, when we simplify our radicals, we also can't have fractions inside the radicand. So we know what to do with negatives, but what about fractions? Well, we fix those with something called the quotient rule. And the quotient rule just says that if you have a fraction on the inside of your radical, you can split that up into the root in the top and the same root in the bottom. And so that allows us to fix cases where we have fractions inside. Let's take a look. The square root of 7 over 64, that violates our second criteria. We got a fraction in there, we can't have it. So all we do is we apply the quotient rule and say, oh, a square root of a fraction is just the fraction with those square roots. That becomes the square root of 7 over the square root of 64, and that's good news because we know what the square root of 64 is. That's 8. And so this becomes square root of 7 over 8. Notice that this is not simplified because criteria 3 says no radicals in the denominator, and we have one. Fortunately, we can get rid of it because we know what the square root of 64 is. And now it's simplified. No powers too big, no negatives or fractions inside the root, and there's no roots in the denominator. Okay, one more. The square root of 15 over 49x squared, that's definitely a fraction in our radicand, so we split it up and see if we can go from there. We get the square root of 15 over the square root of 49x squared. But we know what the square root of 49x squared is. This becomes the square root of 15 over 7x. Or since we don't know that, that x is a positive real number, we would say 7 times the absolute value of x. I want you to take just a minute and do c. Simplify c there. Okay, well, the cube root of 10x squared over 27y to the 6, we can break that up into the cube root of 10x squared on the top over the cube root of 27y to the 6 in the denominator. And that's good news because although we can't do anything with the top, 10 has no perfect cubes in it and x squared doesn't escape. So this top stays the same, cube root of 10x squared over cube root of 27, we know that's 3, and the cube root of y to the 6, the y escapes twice, and that's y squared. And we're done. Hopefully that's what you got. No absolute value signs there because that is an odd index. Okay, I would like you to do these, but I'm going to give you a hint on the first one. Before splitting this up into two separate roots, always look at the fraction inside and see if you can rewrite that fraction by doing some canceling. That makes all of our other work easier. So in other words, I'm going to, before I split it up, think about this as being a simpler root. This is the cube root of Now we've got a 27 down below. We can't do anything about that. But look at this. We've got b to the 10th over b squared. We know what b to the 10th over b squared is. That's just b to the 8th up in the numerator. And look at this. We've got y squared over y to the 5th. We're going to get some canceling there, and we're going to have y to the 3rd in the denominator. So now you can simplify it pretty easily. That's the cube root of, we'll split it up now, b to the 8th over the cube root of 27 y to the 3rd. Now in the top, that b will escape 2 times, and you're going to be left with b squared times the cube root of b squared over, and the cube root of 27 is 3, and the cube root of y to the 3rd is y. And there we go. Everything upstairs escaped. We got our exponent smaller than the index. We got our fraction out of the radicand, and we don't have a root in the denominator. So we're all done. So you now go ahead and give that same treatment to the second fraction shown there and unpause when you're ready to see that solution. Okay, so in this one, we're actually already given 2 separate roots, but we have a root in the denominator. We can think about that as being one big fraction so that we can do some canceling. So that's negative 432x to the 5th over 8x. Now, there's some canceling there. Let's go down here. That's the same as the cube root of. Now, negative 432 over 8. That turns out to be negative 54. And x to the 5th over x, that's just x to the 4th. So in fact, when we treat it as a fraction, the entire denominator cancels off. And now we just have one radicand to simplify. So we saw the prime factorization of negative 54 a little bit earlier, and so that becomes negative 2 times 3 to the 3rd. I won't redo that, x to the 4th. And then we're home free. The negative slips outside. The 2 is going to have to stay inside. The 3 escapes, and x escapes, but leaves one x on the inside. And so we end up with negative 3x times the cube root of 2x.
Okay, well that gives you everything that you need in order to be able to simplify roots, which we'll need for our last 2 lessons, our next 2 lessons, where we'll solve quadratic equations and often end up with roots like these that need to be simplified. So all those depend on this key idea that we can take a root and break it into its individual products and simplify the part that has a perfect square or a perfect cube and is simplifiable. So go ahead and do the assignment for this lesson. As always, let me know or stop by the Math Center if you need any help. It's an important skill, but we'll be using this in the next lesson. We'll see you there.